Okay, class, now we're going to talk on the structure of a nerve. The reason I'm showing you the structure of a skeletal muscle, which is not a nerve, is because you're going to see a lot of similarities with the structure of a nerve and the structure of a muscle. The structure of a nerve and the structure of a muscle. Both of them can do conductivity. Both of them need to insulate their fibers like an electric wire so that there's not cross reactivity, what we call short circuiting. I'll call it short circuiting. All right, so let's see what we got here. All right, so when you look at a nerve, first of all, what is a nerve? It's a group of axons in the peripheral nervous system. That's the technical. A group of axons in the peripheral nervous system. Okay? It's a cord-like organ of the peripheral nervous system, a bunch of myelinated, enclosed by connective tissue, just like a muscle was. All right, so let's look at the components of this. All right, around the whole nerve is called an epineurium, just like around a whole muscle was called what? An epimysium, connective tissue covering. Then the axons are separated within there into a fascicle, groups of fibers. Same thing you did here. Fascicle. Same thing. And just like here, you had a perimysium around a muscle fascicle. What do you have here? A perineurium around a nerve fascicle. Then what did we have with muscle? Each individual muscle cell was surrounded by an endomysium. Each individual nerve fiber, axon, is surrounded by an epineurium. And here's your blood vessels, just like you had in muscle there, blood vessels. So you see, it's very similar because both of these entities do what? Conductivity. Here's another picture. So in this picture here, you can see, and we'll blow it up a little bit. You again can see the same thing you saw over there. We're taking a spinal nerve here in this case, a spinal nerve. Blow it up just, actually I'm going to do it this way. So we're taking a spinal nerve, and you can see here that it's the same setup there. I'm going to make this a little smaller for now. That you had an epineurium around the whole nerve. Fascicles would have a perineurium, and each individual axon, see here the swan cells, would have an endoneurium. So it's really the exact same. We're taking it right off the spinal cord, that spinal nerve. When we had 31 spinal nerves? 31 spinal nerves. All right. So again, structure of a nerve, cord-like organ, connective tissue coverings, endoneurium around each here, perineurium around the fascicle, and epi around the whole nerve itself. Okay? All right. Classification of nerves. Most nerves are mixtures. See, all these fibers, some of these fibers could be afferent and some could be efferent. Some could be autonomic neurons, some could be somatic neurons. So nerves are mixed. Most nerves are mixtures of afferent, efferent, and some somatic and autonomic. Pure sensory or motor nerves are rare. Like a pure sensory nerve, when we get to the, in a moment we're going to talk about the cranial nerve. Pure sensory nerve would be like your olfactory nerve, where you smell from, or your optic nerve. Pure motor nerves are rare. Okay? Pure motor nerves are rare. Okay? Like the oculomotor we'll talk about. In the types of fibers, somatic and afferent, efferent, peripheral nerves are classified as cranial or spinal. Remember, we had 12 cranial nerves, bilaterally 24, and we had 31 spinal nerves coming off. Remember? Okay. A ganglia, remember, let's go back to our definition of what a ganglia was. Way up here. A ganglion is a group of cell bodies in the peripheral nervous system. A group of cell bodies in the peripheral nervous system. So I come back here. So a ganglion, see, this is ganglia because it's plural. They use it, but ganglion, neuron cell bodies associated. Now what you have is this called the dorsal root ganglion. Let me pull this over. The dorsal root ganglion, I'm going to go back here to the spinal cord. The dorsal root ganglion is this area right here. Let's see if I can't get to it there. All right. This swollen area right here has pseudo-unipolar neurons. Go back and study that. Pseudo-unipolar. And you have a cluster of those. So right here, you have a cluster of neuron cell bodies in the dorsal root. A cluster of neuron cell bodies. This is what brings the sensation in. And this right here is called the dorsal root ganglion. The dorsal root ganglion right there. It's a cluster of neuron cell bodies. Then we even have some autonomic ganglia, but we'll talk about that like they show in chapter 14. We'll be doing that. But here's the dorsal root ganglion here, right there. And we'll talk about autonomic. But the key is a cluster of neuron cell bodies, what? In the peripheral nervous system. That's a ganglion. What else we got here? All right, right here, we call it regeneration of nerve fibers. Okay, now I brought this up before. Let me find it for you. I brought this up before when I talked about, let me find this thing here. There's that. Okay, this is what they are showing there. I'm going to bring this down a little bit. But I had brought this up when I talked about something called Valerian Regeneration. Let me find that for you real quick here. Valerian Regeneration. Where did I put that? And it had to do, I was mentioning, if your finger got severed. Yeah, here we are. Valerian Regeneration. Okay, Valerian, this is an eponym, has to do with regeneration of neuron fibers if they get cut. Now remember, neurons cannot do what? They cannot multiply, right? They cannot do mitosis. But if you cut at the axon and it's not too damaged, it could regenerate. Just the axon. Not if you kill the nerve cell body, it's not going to work. If you kill the neuron cell body, it's not going to work. Listen to me. It has to be a cut at the axon that's not too bad. So let's say here's a neuromuscular. So this is somatic motor neuron. Okay, you got cut right there. Let's say severed. Either the whole finger or you cut into the finger so that you severed some of the nerve cells going to your muscles in your fingers. I'm just using that as an example. Then the distal part here, see the cell body, remember, gives the nutrients to the axon. The cell body does all the protein synthesis and everything. So if you cut it, this distal area is going to degenerate because it no longer has nutrition coming from the cell body. So it's going to degenerate. But if things are not too bad, and if you keep the myelin sheath and the epineurium, see, here's another thing. You're keeping a covering. So within that cone of the covering, you may be able to regenerate. Now, when the regeneration occurs, it's kind of like this picture here. It goes in all directions. Sometimes, some of these will try to regenerate, and this forms, look up the word, a neuroma. So sometimes the regeneration can give you tremendous pain if it's a sensory. This is a motor. These neuromas could swell and we have to cut them out. But if the regeneration is good and can go straight down that sleeve within the remember the endoneurium, which would have been around this, the endoneurium, then you might get a good regeneration. So mature neurons, as we say, cannot mitose. If the soma of a damage is intact, okay, axon will regenerate. What's the soma? Cell body. Axon will regenerate. Now, not all the time. You're getting a little bold right here in this text. Involves coordinated activity among macrophages, removal of debris, Schwann cells, which were these, and growth factors. Remember, we talked about growth factors determine how this would go. This neuron, this axon here is growing towards growth factors, but it's inhibited going towards the non-growth factors. CNS bear growth inhibiting that prevent CNS fiber regeneration. See, the CNS, you can't really regenerate. Now, we're working on putting stem cells there. Now, listen to me. We're trying to make it regenerate, but it's not going to do it on its own. The CNS oligodendrocytes. One reason it might regenerate, see, when you're in those tracks, think about it. You could send the signals to the wrong. I can kind of understand why the creator didn't do much with the brain and with the spinal cord, because you could cross circuit and send things the wrong way. But on the peripheral, hey, it is what it is. All right. So anyway, this is kind of what happens. The endoneurium, see that endoneurium? And here's the Schwann cells. Then this thing starts degenerating on the distal. Let's go to this picture. Degenerating on the distal, droplets of myelin and so forth. The axon becomes fragments at the injured, but on the distal aspect, not up in here, but on the distal part, because it's cut off from the nutrients of the cell body. Then macrophages clean out the dead distal of the injury, the distal again. And axon sprouts filaments, which would be this, regeneration, and you're trying to see which ones can make it. And there we are, if it regenerates. If you're lucky and it regenerates. Not all the time it does that, but it does have the capability. But the key is, the cell body is gone, it's not going to happen. All right? Thank you there.